First off, thank you for even attending, right? You could be anywhere in the conference, but thank you for coming here to listen to this. Oh, thank you for the people who stayed. We appreciate that. So my name is Jovonni, and I'm a DevRel engineer for Agoric. And so today we'll be talking about writing async cross-chain smart contracts. Yeah, no problem. Thank you. So, okay, clicker. Okay, maybe the clicker doesn't work. That's okay. Oh, okay, got it. All right. So here's the agenda today and what we're actually going to go through, right? So we're going to go through some Agoric foundations really quick. We're going to go through some basic concepts, writing contracts, upgrading contracts, and orchestration contracts specifically. Okay, also we have, you'll have access to these slides. They're public already, so you can have fun with those. So, but just to show you what we will end up getting to, right? We're going to show you something that looks so elegant, but is doing a bunch of cross-chain magic that is previously seen as almost impossible to do. So let's start with foundations first. Well, first off, how many people in the room are programmers here? I see people with their laptops, okay. We have a few, all right. How many people know JavaScript in here? Okay, good, awesome. All right, so what is Agoric, right? So Agoric is a smart contract platform, right? Partly built using a Cosmos SDK with a bunch of other cool stuff. You write contracts on Agoric in JavaScript. And we follow something known as this object capability model, which we'll explain here in a bit. And then we have this notion of something called hardened JavaScript, which pretty much tries to solve some really nasty things that JavaScript is inherent to. So this is a blockchain conference, so I'm not going to teach you what a smart contract is. I'm just going to rebase your knowledge of, so we have a common language, right? So we like to think of smart contracts as a contract-like arrangement that expressed in code where the behavior of the program enforces the terms of whatever this contract is. So you might not get that definition in a lot of other places, but it helps to kind of set the tone here. So let's start with what are object capabilities. Who has ever heard of this before? Raise their hand. Okay, cool. So just think of these, right? So think of these lines here as permissions, right? And so essentially what this is saying is that Bob has no access to this object, Carol, but Alice has access to Bob and Carol. So what this is saying is that Alice can pretty much give permission to Bob to invoke Carol, right? And so essentially this is a fundamentally, this is a model that it's kind of fundamentally different from object-oriented programming in a sense where in object-oriented programming, if I give you an object, you can invoke any public function on this object. But also, you can, in certain languages, you can forge a reference to an object if you have access to memory, right? And so with this object capability approach, Bob cannot forge a reference to Carol. Therefore, Bob can't invoke Carol unless he's explicitly given the permission to do so. So this actually serves as a really nice security foundation for a lot of interesting things. So how many people know how buggy and nasty JavaScript can be? Right? Okay, there's a few of you. So high level, what hardened JavaScript is doing is just trying to fix this issue of JavaScript being malleable. So, and actually the next slide is a better example. So here you go. So if you look on this side, this is without hardened JavaScript. If you look on this side, this is with hardened JavaScript. So what you see here is we have this that we're making, and what we can do is we can overwrite a property of the object that's returned from this. In regular JavaScript, you can do this the same way that you can do array.prototype push and declare a new push function there, or just declare whatever you want there. But this will work in regular JavaScript, but when you use harden, what happens is it makes it where you cannot overwrite or change the properties of this object. It freezes the properties of this object, therefore solving a lot of issues that JavaScript inherently has. So this is the high-level idea of what you actually get when you're using hardened JavaScript. So just a little bit more foundation. Remember, these contracts are just JavaScript, right? So your state in your contract, you can treat as if you're just writing JavaScript in general, for the most part. And we have some extra things that kind of help you with this, but I want to remind you that this is just JavaScript. So now let's get into some interesting stuff. This is what's known as a quintessential hello world in Agoric. So what you notice is we have this start function here. And how many people know Solidity in here? Probably a few of you. Okay. So this start function is akin to a constructor in Solidity. If you know Cosmosm, it's also akin to the instantiate function or entry point in Cosmosm. The point is that this is the entry point of your contract when you define it. Okay. Okay, now let's talk about access control, right? And if you think back to our object capability model that we talked about, access control is kind of an inherent property of using this paradigm. So you see here, we'll kind of talk about what these public facets are, right? But the point here is we have this function here that is returning to us an object, and that object that's being returned is what allows us to invoke certain functions. So this specific thing that's being returned here, whoever gets to use this gets to invoke this function. Whoever gets to use this thing that's returned here, and we'll talk about what these are, gets to invoke these things, right? And so if you see here, this is saying that this thing that allowing someone to invoke it or invoke the functions that they can get access to from this thing has now the ability to invoke these two functions up here. That's pretty much high level of what you're actually getting inherently when you use this object capability model from an access control perspective. Okay, almost done with foundations here. So in Agoric, we have this thing called VATs. And hopefully you recognize this. This is from JavaScript Mozilla docs. But essentially, what a VAT is, think of it as an isolated environment for JavaScript execution, an isolated JavaScript execution environment. And so in this environment, just like any other JavaScript environment, you have a heap, you have a stack, and you have a queue of messages. And then you have an event loop that is pretty much listening to this queue, and this event loop is responsible for getting messages or keeping, it's pretty much your active thing that's acting in your environment to ensure that messages are being picked up and sent to where they need to go, right? But this stack allows us to push, when we want to have functions in our environment, we can push these functions to the stack with their parameters, et cetera, and now you have a stack machine, essentially, that you can now access, that you can now use all of these things to have a full computational environment. And so the reason why we call it a VAT is because it comes from this philosophical idea of how do you know your brain is not just in a jar wired up to a computer and the computer is tricking your brain into thinking that you're alive. But essentially, this is a key part here. Contracts run inside their own VATs, and you can think of these as processes in an operating system. Let me see. Okay. Oh, this is also key. Inside, any communication that's happening inside the VAT is synchronous. When you're doing communication between VATs, it's asynchronous. This will come in handy here shortly. Okay, so now you just got through foundations. Now you know about Agoric foundations more than a lot of people on the planet. Now let's get into some more interesting stuff. So these basic concepts we're going to introduce you to, which will give you a really good ground understanding of some of these newer concepts that we introduce and we use as like core primitives in this environment. So we're going to talk about a brand, a mint, an issuer, a facet, an amount, a payment, a person, and an asset kind. Okay, so first let's talk about a brand. So a brand represents a unique identity of a type of digital asset. And so you can think of this as USDC, any asset you can think of. And so here you see that we get this brand from this thing called a token issuer, and we'll talk about what that is. But a key thing here is that it's associated with a specific mint and a specific issuer. This is key. So this next thing here is an amount. So typically in Solidity, if you want to send an amount of tokens around, you just use an integer. And this integer is representing like a value, right? But we have an abstraction for this, which actually helps in this whole environment, given some of the properties. So essentially, with an amount, what you're doing is you're specifying what brand, and you're also specifying the amount of that brand that you want to actually represent in this amount. And so this represents specific quantities of digital assets, but this is key. Amounts can describe either fungible, non-fungible, or semi-fungible assets. Who in here has never heard of a semi-fungible asset before? Okay, for those who don't know, a semi-fungible asset is, think about like concert tickets. Imagine a concert ticket that the ticket is only saying what section you sit in. So if you have 20 sections in a concert venue, everybody who sits in the same section, their tokens are pretty much interchangeable or fungible, as we like to say. But anyone who sits in section 5 and section 6, their tickets are not, equal, or they're not fungible. So now we move on to an issuer, and here you see something like we give these convenience. You'll see conveniences like this all over the environment, where you call this kit thing for make issuer, and it gives you a brand new issuer and a mint. It's like a convenience for you. But essentially, an issuer is responsible for validating and managing a specific currency. And this is key. An issuer is a trusted authority that validates payments. And you'll kind of see what this means here in a minute. Okay, let's move on to a mint. So a mint, it creates new instances of digital assets, such as a new currency, blah, blah, blah. But this is key here. Only a mint can issue new digital assets. And also, a mint has a one-to-one relationship with both an issuer and a brand. This helps with you reasoning about any type of contract that's doing anything interesting, because in Solidity, sometimes it's not sure where something is being minted from, right? But it's explicitly represented in the primitives of the environment. But you see, so we're building on what we learned already. So we're getting a brand issuer and a mint. We're making an amount here, and then we're using the mint to mint a payment. And we'll talk about what a payment is. But you see, the minting of a payment is using an amount. Okay? So now let's talk about payments. So payments are spendable representations of a digital asset, and it's a unit of digital assets created by a mint, can be transferred between purses. And so what I'm showing you is the same code over and over. And so you see this payment, we're getting a payment here. Now let's see what we can do with this payment, which brings us to this notion of a purse. And if you start to realize the nomenclature represents real-world things that help you remember what the thing is doing. Because if I asked you what's a purse, you probably have a good approximated answer for the real answer. So you've seen up to here before. So we're using a mint to make a payment. But then what we're doing is this purse that we make, notice how we make an empty purse. And what we do is we can deposit into this purse and we can withdraw from this purse, the same way that your mom puts money in her purse and takes it out. But we'll see why this is interesting here in a minute. Okay, and last thing here is this asset kind, right? So we talked about fungible tokens, non-fungible tokens, and semi-fungible tokens. But the way we represent them is fungibility. We have this natural number here. And then we also have this copy bag. And the reason why it's a copy bag is because it allows for duplicates, right? But if you wanted to make NFT collection in general, you just would have no duplicates in there. And it would be functionally equivalent to that. And so when we actually make an issue or actual asset, all we're doing is specifying what type of asset kind it is here, right? And the system knows what to do with this, or the environment, I should say. Okay, almost done with this part here. So this is a facet, and let's spend a little bit of time on this, right? So if you think about a diamond, what is a facet? It's these things, right? And if you look through one, you can kind of see inside the gem, right? Same kind of concept, because these facets, and notice you've seen this code already, these facets here allow for us to access the internal world of this start function. And now we can start programming how you access this, what's being accessed, etc. But the point is that you can have facets, and we'll go into facets a little more deeper later, but you can have facets for different purposes, right? Depending on if you want them to be widely shared or not. Okay, so now you just got through section 2. We went through very basic foundations. Now you went through basic concepts. And the difference between a foundation and a concept is foundations is kind of like prereqs, and the basic concept is like your 1 or your 100 level class. So now let's look at what actually writing contracts look like, right? I showed you code several times. Let's look at what you have to think about when you write contracts. But first, we have to talk about this concept known as offer safety. So think about it. If you make a deal with somebody and you make an offer to them, it's only fair that you get exactly what you want to get, or you get a full refund. And so what Agoric does is we have a service on-chain, which we'll talk about in a minute, that guarantees this notion of offer safety. So formally, we say offer safety means that the user is guaranteed to either get what they said they wanted, or get a full refund for what they offered. So this brings into account this thing that we call Zoe. And so we'll talk about what Zoe is, but fundamentally Zoe is a framework that provides a way to write smart contracts without having to worry about offer safety. So we'll talk about what Zoe is, what's an offer specifically, what's a proposal, an invitation, and a seat. And once again, you'll see this trend of the nomenclature trying to communicate to you exactly what the function is. So high level, Zoe is a service on chain that in a smart contract API that's designed for trading assets to reduce risk, right? Okay, but more importantly, let's look at what the flow here is. So you have a contract here. This should be Zoe right here. I'm not sure what's going on there. Okay, but imagine a box right here that says Zoe. That's so strange. Huh. It's the color. That's funny. It shows on my computer. But anyways, there's a box right here that says Zoe. Okay. So high level, these parties, what they do is they escrow these assets into Zoe. And you can think of Zoe as like an enforcer of guaranteeing offer safety. So these parties who want to do a deal, they escrow their assets into Zoe. Then what happens is the parties then communicate with the smart contract. And so here you see the communications that happen here is assets, and the communications that happen here are information. So what happens is the parties communicate with the smart contract, and the smart contract runs its custom logic. And so after it runs its custom logic, assuming everything pans out, now the contract signals to Zoe to reallocate the assets. So user A and user B now have their assets swapped by Zoe. They don't receive them yet, but Zoe says, okay, the deal is going well, I'm gonna swap them, but Zoe hasn't done a payout yet. So after the reallocation happens, what then happens is now the smart contract signals to Zoe to complete the offers, and then finally Zoe now allows the parties to receive their payouts, which is the result of doing that swap. Okay? But you see Zoe's acting as like an enforcer here to make sure that people get what they want or get a full refund. So this brings into, now we talk about this notion of a Zoe contract facet. Now this is just the API object for a running contract instance, meaning an instance that is existing, to access the Zoe state for that instance. And so the real takeaway here is that in your start function, this entry point that we talk about, you have access to this ZCF here so that you can use it for your convenience during the execution and lifetime of your contract. So now let's talk about what a proposal is, and this is a very key concept. So proposals, when you interact with a contract, the way you interact with it, including in that way, is a proposal. And this is the structure of a proposal, but let's talk about what these properties mean. So this give property of a proposal is representing what the party is trying to give up, the asset, and this want is the opposite of what they expect from the deal. This exit criteria is pretty much the party being able to specify under what conditions the offer can be canceled. So it can be, you can specify if you want the offer to be canceled on demand, you just waive it where the contract now has all of the capabilities to cancel the offer. To cancel the offer or the deal pretty much. Or you could set like a timeout where after this timeout, now the offer is automatically canceled. But this is optional here, and this actually just defaults to on demand. But you will see how this is used. So now we talk about what an invitation is. And so to interact with a contract, you must have an invitation that allows you to do so. And so one thing to keep in mind here is, remember we talked about payments earlier, but an invitation is an actual payment. So I can treat an invitation like an actual payment where I can put an invitation inside a purse the same way that I would with any other brand. It's very key because you can treat the right to invoke a contract as an asset itself in a lot of ways, which is a very interesting concept that you really don't see in a lot of places, but it allows for some interesting properties of building dApps in this way. So like I said, it's necessary for joining contract instances. This is key here, that is created by the contract, and we'll show you what that looks like here, as needed for new participants. Okay, I think that's good there. Okay, now let's look at what it looks like in code, because I want to keep showing you code to make it more concrete for you. So you've seen this before. This is a proposal that we talked about. So now look at this. First, I'm asking Zoe to give me a public facet for a contract instance that exists on chain. So it's saying, get me the public facet, meaning get me a way to peer into this environment of this contract. So I take that public facet, and I now want to invoke this method on this public facet in an asynchronous way. And we'll talk about what this E thing means. But I get an invitation to trade. Then I use that invitation to make an offer with Zoe, the same way that we're showing you through that graphic, to make an offer to this contract instance via Zoe, using that invitation with my proposal that I made. And essentially, and you look back at the graphic, you have this notion of getting payouts after the deal is done. Remember, we talk about in the end, that step 6, that Zoe now allows the parties who are participating in the deal to now get payouts of the deal. Okay, and this is key. So we create an invitation there to trade, submit the offer, proposal, and use an invitation. So, and also keep in mind, these slides you will have access to. So you'll be able to go back and study these. So don't worry too much about understanding every line right now. But what I do want to assure you is that all of this code that you're seeing works. This is not fabricated stuff. Okay, so now let's talk about what an offer is. So in order to invoke a contract, I have to submit an offer to it with all of these things I mentioned. And so you've kind of already seen this, but we're just going to say for concretion, offer has an invitation, a proposal, payments, and offer args, which is actually optional. But that literally ties that all together for you. Come on. Clicker's going haywire on me. Okay. So this is literally the exact same code I just showed you. But this is just showing you, I kind of jumped ahead, but this offer here, remember we have invitation, proposal, payments, etc. Okay, almost done with this third section. Be proud of yourself. So we have this notion of seats in Zoe, and let's spend some time on this. So Zoe uses a seat to represent an offer in progress. This is key. And so we have 2 different types of seat facets is pretty much 2 views of the same seat. So you have a ZCF seat for the Zoe contract facet, and you have a user seat. And we'll show you what that looks like. But high level, this is used within the contract, and I'll show you that. And this is used when you make an offer to a contract, you get a seat in return. Okay. So this is an offer handler. And you see when in my offer handler, it's actually receiving a seat as one of the parameters. And that's a ZCF seat that I can now do things with. I can get the proposal from that seat. And see, I can exit this seat here. This is actually a ZCF seat too, because you get a ZCF seat when you take a mint and you mint gains, which is just kind of minting more. You get a ZCF seat, so you can also do exit on that as well. But this ZCF seat is still another view of the same seat. This is just inside the contract. And in the user seat, like I showed you before, and keep in mind, I'm showing you the same code over and over, so that is familiar to you. This is the user seat that you get after actually making an offer. Okay. So, okay, now let's talk about offer handlers, right? So when you make an offer to a contract, that offer has to get handled by something. You can think of that offer handler as an actual function. And so handlers are responsible for handling any offers, like I just mentioned. It accepts a ZCF seat. You've already known that. We've shown you that already. And don't really care about this. The point is that there's a function that the offer is then handled by. Key part here. Okay, and then the private args, these are optional arguments, but this is key. You pass private args to while you're creating the instance of the contract. So, for example, let's say if I want to ensure that my contract has access to something during contract creation time, right? I can pass that through my private args here. And so essentially, I mean, this is a good example too, like to share minting authority among multiple contracts, we can pass an external mint object, right? So you can pass that during contract creation time, but it's optional, right? You'll kind of see examples of using private args here. Okay, so this is the last thing on public facets, because we talked about what a facet is. Let's talk about the difference between a public facet and a creator facet. So essentially, this is the key here. With a public facet, it's the intention. You intend for it to be shared with as many people as possible. But with a creator facet, you intend for this to be shared with as few people as needed. And so really you can you can categorize these by the intent on what you want to be done with that. Sometimes the clicker works, sometimes it doesn't, okay? So think about like a deal in business, right? Terms of a contract. And so let's say if you had a contract and you wanted to, let's say a contract is like a store, like a Shopify store, and in your contract, you want to specify inventory, you can put that inventory in your terms so that you can retrieve that during like the contract's like lifetime. Because in the actual contract, go back. So in the actual contract, you can invoke Zoe to get the terms of that instance. Well, this is from outside, right? So you can get the terms through Zoe in a few ways. Okay? Okay, so remember what I said in the beginning, inside of a vat, communication between objects is synchronous, but between two vats, it's asynchronous. Think about like an operating system and two processes communicating with each other. So we ask ourselves, how do vats communicate with each other? And so that's where you've seen this thing throughout the whole talk, this notion of E. How many people have ever seen this before? Because this goes back, way back. Okay, good. Nobody. So think of it like this. We said you guys know JavaScript. So how browsers use fetch for remote communication. In Agoric, we use this thing named E, and this really is for an eventual send. And so essentially what it's doing is it's asynchronously invoking a method in another vat, machine, or hint, blockchain. And so essentially this whole environment of like using E, et cetera, you can actually use this not even in the blockchain world. You could just use it to have two remote objects really talking to each other in this asynchronous way. So it's really bigger than just Agoric, right? This right here actually has a really interesting history if you're ever interested in getting into it, but talk to me after if you're interested. And there's some other people here who will probably talk your head off about it too. So, okay, but to make that more concrete, remember we have this thing called Zoe, right? We talked about that. Because Zoe is not in the same vat that our contract is in, we cannot speak to it synchronously. This is a synchronous call here. So we have to invoke it this way, where this is an async call. And then, because it's JavaScript, remember, that's a trend here, it's just JavaScript. This is a promise, and then you can do the same convention that you do in JavaScript with like then and catch, etc. Okay, so, and this is also key to understand. So when we're invoking this way, what we're really doing is we're invoking a local presence of that remote object. So programmatically to you, you feel like you're invoking something that's synchronous here, but it's a lot of other stuff happening in an async way. But the point is that you're interacting with this local presence of this remote object. So that's key. And essentially, like this may not be formally, but it's pretty much acting as a proxy for that remote object. Okay? And key here too is this facilitates communication across different machines or VATs. Remember, that's not blockchain specific. Okay. So let's talk about something else that we have on chain. If you look at our Golang code or the Cosmos SDK part of what we did, we have this Cosmos SDK module we built called vStorage. And so essentially, this is how we treat persistent storage to be accessed by the world, and this is how we represent it. So on this side, this is really just helping you see how it's hierarchical. And what I mean by hierarchical is, how many people are familiar with IAVL trees and Cosmos SDK, or just in general? Or just a tree in general, okay. So in general, with a tree, imagine you have a tree, that root node, if you go down the tree a little bit, whatever node you stop at, if you want to write to children in that tree, you can't access the rest of this tree, right? And so what this really means is that this hierarchical data storage that's dot separated, and we'll kind of show you what that looks like, it's because it's a tree, when you give a node to the contract to actually use, it can only write to children from that node you gave it and down. Okay? Let's look at, okay. This is the most key thing you need to understand about vStorage. So contracts can only write to vStorage. they cannot read from vStorage. But clients read from vStorage. But let's look at what a graphic says, what this shows here, right? So essentially you have a contract that's writing, and this contract is writing to a specific storage node for a key, and it's setting this value. After the contract does that, then a client can then make an RPC call to the chain, to vStorage specifically, to fetch a value, and the value is passed back. And you can do that a few different ways, actually. I'll show you. So this is, remember when I talked about the tree, right, and how you have children in this tree, and you can store from a child and down from the root node, well, from the node that you're given. So really, if the contract is given a node, the contract will treat that node like a root node in the tree, and can only store it to children. So what I'm doing here in my start function is this storage node that I'm passing in my private args, we talked about that earlier, I'm making a child node there called metrics, which I can then store to, right? So if I'm doing this set value here, this is storing at the metrics node and down. That's key to understand. Okay, and you can do it a few ways. You can do it through a CLI, but doing it through the CLI is just it's creating this RPC call for you, right, just as a convenience. But because you guys know JavaScript, like you said, you can also do this just through a pure RPC call, like regular JavaScript. Okay? All right, you just got through 3 sections. You got through foundations, prereqs, you got through basics, and you got through writing contracts. So now you know how to write contracts on Agoric. Now let's talk about something that's even more interesting. Upgrading contracts. So how many people said they know Solidity in here, just to be sure? Okay, few people. In Solidity, you don't have this notion of upgrading contracts. What typically happens in Solidity is you have a contract, a proxy contract, and that proxy contract has an implementation contract somewhere else that it points to. And so when you want to upgrade the contract, what you do is you then change the pointer, you change where the proxy contract is pointing to, and you treat that like an upgrade, but you're not actually overwriting code. That's key. Cosmwasm is a little different with migrations, but this is very different. So there's 2 different types of upgrades in upgrade types, right, that we support. So the first is known as state-based upgrade. And fundamentally, this is keeping the contract state during the upgrade. And replay-based is different because replay-based, let me walk through this. So imagine you have 2 functions. One is calling the other. And when it calls that other function and it gets a message back, imagine there's something that's logging that interaction. Then when you want to upgrade, this something that's logging it, all it's doing is replaying the interactions between those 2 objects to arrive back at the state that it was before the contract tried to be upgraded. So essentially, this is 2 different ways of upgrading, which are very different, but this actually solves a long-standing problem in the space. It's a very new thing, so it's moving pretty quickly, but is this difference making sense? You can think of this as like a refrigerator, just holding your food in it, but you can think of this as like a recipe. And shout out to Mark Miller for that analogy there. Okay. Now, why upgrade a contract? This should be obvious for everybody in the room, though, right? I mean, you have bug fixes, feature enhancements, right? Typically, in the Solidity world, you got a V2 coming out that's the reason to upgrade. You have improvements for performance and compliance reasons. You guys get this slide for sure. Okay. Now let's talk about stores a little bit. So stores, these are specialized data structures used to manage and persist key value pairs or sets. And there's 2 different types of stores that we like to really talk about. So you have map stores and set stores. And if you just take away the stores word, this will help you understand what they are. We all know what a map is in this room, right? Key values. And we all know what a set, key property of a set is no duplicates. And so essentially, these 2 stores are very basic for you to understand, but you can think of this as a wrapper around a JavaScript map, right? Like I said, if you take away this helps you understand what it is, but a key thing is that there are also other store types that we can support here. Okay, now let's talk about baggage. So early in the presentation, I show you this start function several times. One of the parameters of this start function is something we call baggage. So baggage is a map store, you guys just learned what that is, that provides a way to preserve state and behavior of objects between incarnations or contract versions in a way that preserves identity of the object so that if something else is trying to talk to that object, it doesn't get confused about which object it's trying to talk to. And so we have this convenience that we give to developers of this zone API. It's a way to manage durability, and we'll kind of look at that a little bit. But this right here, what it's doing is underneath, we use this thing known as this provide pattern, which is like fetch or create, where if you want to, if you use this, it's going to see if this exists, and if it doesn't, it's going to create it underneath, right? You could do it yourself, but this is just a convenience for you. But why is this important? This is like, I could tell you all the stuff in the world, but why is this important? So this approach to contract upgrades preserves access to objects to ensure that the contract does not violate, remember you learned this earlier, this object capability security model. So before and after upgrade, you have no more access and no less access. That's the key thing here. Okay, I hope you guys like this picture. This is something we know that we call an exposed remotable model or exposed remotable object or EXO. So just think about image first. This outer shell here is a protective thing. You guys know what an exoskeleton is. You guys like sci-fi, right? Okay. Think of this thing as a protective layer. In the middle is the things that you actually really care about. So exos have this notion of an interface guard, and you guys program, so you know what an interface is. The interface just ensures that whatever is implementing this interface adheres to the function signatures and what it's supposed to be, the return values or return types, etc. This interface guard, and we'll look at on the next slide how it looks. This interface guard is going to protect what is being called from this exo, or what is being called that is in this exo, and this interface guard is going to protect the input to that call and the output. So let's actually look at the concretion of that. So here you have a public facet. We talked about this, but we're making one using this approach, using this zone, creating an exo from this zone. And the zone is key to understand that this is used to allocate exos. So here we're going to name it. This is my interface guard. And so what happens here is I'm saying that if someone calls this, it shouldn't have parameters, and it should return this type here. And here I'm actually designating what the function is that can actually be called. So here's another example of it. Well, here's a visual, and we'll walk through another example. So essentially, the user wants to make a call to add function using E. So what happens is the interface guard first is going to verify the method signature. So verify what's coming in or how it's being invoked. If the exoskeleton thing, the thing that's protecting it, is happy, then it's going to make the actual method call. But what's going to also happen is on the return from the actual method being invoked, this is now going to be also checked by the interface guard to ensure that this adheres to the interface's return type. That's key. Then if the interface guard is happy again, then the actual caller gets what they're asking for. So another concrete example, this is, again, how we use EXO to create how we use zone.exo to create one. So I'm naming it. Here's my interface guard. What this is saying is whenever people invoke this make send invitation, it should have no parameters, and it should return an invitation shape. And this is something I'm defining somewhere else, but this could be whatever you want it to be, m.promise, whatever. Then this is the method that that can invoke it, and that's key. Let me see anything else? Okay, no, I think that's good. Okay, so be proud of yourself, because this may seem like a bit of information, but you just went through 4 sections of dense material on how to understand the foundations of Agoric, how to write contracts, what are prerequisites, and how to upgrade contracts now. And I hope you see that the upgrade mechanisms here are not trivial. They've actually been well thought out, and they vary kind of widely from what kind of upgrade patterns you see in conventional blockchain spaces. But I promised you we would get to a destination, and now we're finally here. So now we're about to talk about the actual talk, which is writing async contracts at a cross-chain. So I promised we would get to this destination. Okay, but let's start with the use case first. So the use case is I want to liquid stake my bonded TIA to receive an airdrop from Stride. So you have TIA, which is one chain. You have Stride, which is another chain. So what this is going to require me to do is I have to submit a transaction to undelegate my TIA first. which is going to require me to sign a message in a wallet. So that's one signature. I want you to count signatures. That's one signature. But then also, I have to wait 21 days. Why? Because unbonding periods, right? You have 14 days. It's configurable, right? But you have, with TIA, it's 21 days. So that means I have to sign one transaction, then I got to wait 21 days. 21 days. In contracts, and I want you to keep this in mind, the title of this talk is actually almost an oxymoron, because asynchronous, truly asynchronous transactions or contract calls is not actually a thing, because you have to actually fake it in Solidity. What happens in Solidity is I make a call, it sends some packet to do some cross-chain thing, then something sends a packet back, then I have to, as my contract catches it, I have to send another message out. That's me trying to fake or pretend asynchronicity. But doing something like this would not even work because my contract can't wait 21 days. My contract either runs right now or it reverts. Either completely goes, it's atomic or transactional, or it reverts. So after this 21 days, let's say I wait. Now, what I have to do is I have to now transfer the TIA that I just unbonded, which is requiring me to do a second signature to a transaction. Then I have to invoke native functionality on that chain. This could be any other chain, but it's native functionality on the other chain, which is going to require me to do what? You guessed it, a third. I have to sign a transaction a third time. So there's 3 different transactions I'm signing. Okay, nightmare, but people do it all the time, surprisingly. I don't have to state it outside. I'll just let you read that. It's cumbersome. Okay, hopefully you like this graphic. So in orchestration, we have these concepts of an orchestrator, a chain object, an orchestration account. And this orchestration account is an abstraction for a remote chain account or a local chain account. And you can treat them both the same through the API. Okay, so how many people have heard of Interchain accounts? I'm sure several people. And don't be shy, how many people have never heard of Interchain accounts? Okay, cool. So you can look into this spec, right? But just think of it as an IBC application that's designed to allow one chain to control an account on another chain. You can look deeper into it, right? But that's essentially what's happening. But when you combine it with Agoric, this means that the contract that creates this interchain account now has sole access and control over it. That's key. Let's see why. Okay, so this is more API stuff, right? So this is the interface of this chain object, right? We can make an account and we can get chain info. But you have the same API surface on both a remote chain object and a local chain object. And this is the orchestration account interface, right? Where you can, if you have an orchestration account, which is either a remote chain or a local chain, you can get its address, you can get a balance, right? And here with this orchestration account, you can invoke this send, transfer, or like, this is like one transfer, this is like a series of transfer steps. Okay, trying to get you to the code. Come on. Okay, now this is the orchestrator interface, right? So what you can do is you can call getChain to get a chain object, which then you can do some cool stuff with, and I'll show you. You can make a local chain account and get brand info as my, okay. Let's do some fun stuff, okay. Now I remind you, this is the use case. Come on, clicker, don't fail me. Don't fail me, clicker, please. Okay, this is your use case, just to remind you. Boom, I promised you we would get here. Now, I really want you to take away, because you guys were brave enough to stay, I want you to see the magic in this, and I will not leave until you see the magic in this. Okay, so let's go to the next slide first to show you how it's wrapped. So we have some boilerplate stuff. This boilerplate stuff, you see some stuff that's familiar to you, right? You see a start function thing that has some wrapper thing, right? Don't worry about that. Think of this as your start function, because you're passing the same type of stuff. You know what a zone is, you know what private args is, you know what a ZCF is. So what's happening is when I make my zone, again, I'm specifying what the invitation is going to be for, right? Obviously, you've seen Harden before. You've seen the proposal that the invitation has to match. This is just a proposal shape that the invitation has to match. This is key. I didn't say this, but if you make an invitation and you specify a proposal shape, this means that if someone uses the invitation and their proposal doesn't match the shape, it actually Zoe rejects it before the contract even gets it. It's a good property. Okay, but now let's go to the meat. That's the boilerplate. This is the meat. This is the magic, I promise you. So the first thing I'm doing is I want to stress this. You're going to see await. You've seen await throughout the whole talk, but you're seeing await on cross-chain messages. This is so key because what's happening based on everything I showed you today with VATs and all this stuff, it's simply a promise being resolved by actions happening elsewhere. Unheard of, I have to stress that. So what I'm doing here is I'm first off, I'm passing an account to this function, right? So, this is a key thing here. Before this function happens, it's like a setup that happened beforehand for this test. You have an ICA that was made before, and that ICA was funded, and that ICA delegated some tokens. So then, when we get here, this Celestia account already has a delegation. So when we call get delegations, it's not 0. That's key. So we get delegations in TIA. Then what we're going to do is we're going to undelegate. And now I could easily go on to the next line, but I will miss the magic. Because remember, what happens when I undelegate? How long do I have to wait? 21 days. So it seems trivial that it just does that, progression happens here, but this happens after 21 days. It's unheard of. Then next what we're doing is we're calling this get chain to get a chain object for stride. And we have a thing called chain hub where it's like in vStores, the thing I showed you earlier, is a bunch of these different types of chains we support, and you could just call get chain for that chain. It'll give you a chain object. Then here I'm making the interchain account on another chain. I have to keep stressing this. Then what I'm doing is with the Celestia account that I passed in, I'm getting the balance now because remember, I already undelegated. So this is 21 days after I'm getting my balance of TIA in my account after undelegation. Then what I'm doing is I'm pretty much sending the bulk of my money through a transfer from this Celestia account, this ICA on another chain, on chain A, and then I'm sending it to my Stride account that I just made. So that means from one chain, I'm actually invoking this, sending money to it, etc. Then I'm calling some native functionality here. Okay, and this is a second example, this next one's a second example, but it's the same type of thing here. I'm making these chain objects. You know what get proposal is. I'm making accounts here, which are ICAs. I'm getting an address. And here, I'm just doing some magic to make sure that the object doesn't have any promises in it, that I'm iterating all over properties in there, and I'm depositing payments into that local chain account that I just made. And then, to wrap this up, I'm setting up my transfer steps here, which is I'm saying what chain, what destination, etc. Then I'm doing my transfer steps here, and after my transfer steps are successful, that's when I'm doing a delegation on another chain. And remind you, I'm just handling this as a promise, as I keep saying. Okay, and this is literally just boilerplate that I showed you already, but you understand what these things are doing now, right? So you have your EXO, blah, blah, blah. Okay? So, I know it seems like we got there pretty quickly, but I want to recap what you just learned. And it's very easy to not really see this, but you learned your foundations, basic concepts, writing basic contracts, upgrading them. But this is the magic that I promised you today. Because today you just learned how you can use traditional JavaScript in a new type of fancy thing, like this new beast of a machine. Not new, but to write cross-chain asynchronous contracts that you can then handle from one contract. So essentially, we call this orchestration because you can orchestrate like a conductor. Oh, damn, see the colors are off. But this is a conductor orchestrating blocks, okay, whatever. But I hope that it's easy for you to see that this stuff is unheard of before Agoric. And this is not buzz stuff. I challenge you to go find a place where you can actually do this. And when you do find it, let us know. If you're interested in learning more, please go to docs.agoric.com. And also, if you want to see this talk again, we're giving it again tomorrow, which you maybe can go into more time because it's the only workshop tomorrow. So if you want to go into more details, you know where to find us.